Okay, today we're going to introduce the rush model, and we're going to introduce this from 3 parts. First, let's say some background of this rush model. What is the purpose of the rush model? The rush model is a statistic model used to analyze data from assessments, surveys, and other tests to measure the abilities of individuals. Specifically, the rush model is used to estimate the ability of an individual and the difficulty of an item based on the individual's response to the item. It assumes that the probability of the individual correctly answering an item depends only on the individual's ability and the item's difficulty. The model produces item difficulty and individual ability parameters that can be used to create a common scale for comparing individuals and items. This model also has some applications in fields such as education, psychology, and health research. It can be used to develop and evaluate assessments, measure changes in abilities over time, and compare individuals across different assessments or tests. However, if we want to apply this model, we need to meet some conditions. There are 4 basic assumptions. The first one is every individual has a particular ability. And the second one, each project has a difficulty. The third one, the difficulty of each item can be presented on the same scale. The last one is the difference between the number of response probabilities for any fraction can be calculated. Also, there are 2 objective requirements we need to meet. The first one is the individuals with high ability should be more likely to give correct answers to any question than those with low ability. The second one is any individual should always perform better on easy subjects than on difficult ones. And now we will move to the derivation of the formula. This is the steps at how we derive this formula. First, we need to calculate the percent correct for each person, and this will result in an ordinal raw score, and then convert its percentage for each person into the odds of success by calculating the ratio of each person's correct. Then we take the log of the odds of success to calculate person's ability. This transformation resolves the problem and compression at the ends of the scores. And then we can get the general formula as below, where YIG is a binary outcome. The student G answers question I, and theta G corresponds to the student G's ability, and BI is the difficulty of the question I. When it comes to the application, the right map and the bubble chart are 2 graphical representations of the rush model that can be used to visualize the relationships between items and individuals. Let's say the right map. The right map provides a 2-dimensional representations of how the difficulty of the item is related to the ability of the individual. Through the application of the right map in the rush model is analysis of school test papers, we are able to investigate the relationship between quiz items difficulty and students' ability. Throughout the map, items and individuals are represented by points, and their relative positions on the map reflects their level of difficulty or ability. As a general rule, the items on the map are listed in ascending order of difficulty, and the individuals are listed in ascending order of ability. In addition to identifying items that would be too easy or too difficult for the target population, the map can assist in identifying individuals with extreme ability levels. And then my group member will introduce this in details.
Okay, now we are moving to the part that how we apply the red map in the rush model. We are going to apply the example in the article, the application of Rush model in the quality analysis of the examination papers. In the same larger scale, we can see the left part that's squared in orange represents the person mean, which is the distribution of students' ability levels. Meanwhile, the right part that's squared in light green represents the adult mean, which is the distribution of the difficulty of the total 18 questions showed on the examination paper. The right side of the horizon axis shows the distribution of the difficulty of the items of the examination paper, and the left side shows the distribution of students' ability levels. The middle line is the longitude scale, which is an important medium for comparing the difficulty of the test with the student's ability level. M is an abbreviation of mean, which stands for mean. S is the abbreviation of one standard error, which means one standard deviation from the mean. T is the abbreviation for two standard error, which means two standard deviations from the mean. Okay, so let's see. So on the right side of the map, the 18 items are arranged in descending order of difficulty, with question 5 being the most difficult and question 8 being the easiest one. The pound sign represents a number of students, and their reading ability level is listed from top to bottom in descending order. Therefore, according to red map, it is possible to determine whether the paper presents more reasonable questions. In conclusion, the red map is primarily used to verify the logical arrangement of test questions in Rush model. Let's move on to the bubble chart. The bubble chart, also known as the category response function (CRF) plot, is a graphical representation of the relationship between the item difficulty and the probability of a correct response for each response category of a polytomous atom. Each category is represented by a different colored bubble, and the size of the bubble indicates the portion of responses in that category. The chart can be used to identify which categories of an item are the most difficult or easiest for individuals to represent to, and can help the identification of poorly functioning items. Now, we need to also consider how to apply bubble chart in Rush model. I will show it by introducing our example of the bubble chart from the article, Student Ability Levels and Test Items in Educational Tests, Rush Model Analysis of Difficulty. First of all, I will illustrate the elements in the bubble chart. A bubble chart is a type of chart that displays data in a three-dimensional format using circles or bubbles. The size of the bubble represents the value of a third variable, where the horizon and vertical positions of the bubble represent two other variables. We may say the horizon axis of the bubble chart stands for outfit MSQ, which stands for mean square, and the position of each bubble on the horizon axis is the value of the outfit mean square. The vertical axis of the bubble chart represents the difficulty of the exam questions. The diameter of each bubble indicates the standard error of the corresponding value. Thus, we may conclude each bubble represents different atoms we test respectively. The size of the bubble corresponds to the ratio of the Rush standard error. A smaller bubble indicates a more accurate estimation of a student's ability level. The overlapped bubbles indicate that the difficulty of the items is very similar, which will lead to an unclear item ordering. Ideally, test atoms should be located near the central axis of the bubble chart. And moreover, according to bubble chart, it helps researchers to identify the portion of atoms that are not suitable for the Rush model.
Okay, next I will present the strengths and limitations of RASH models. The RASH models boast a number of impressive strengths that make it a popular choice among researchers and practitioners alike. One of its most notable features is its ability to produce interval-level measurement, granting users a consistent scale across all items. This invaluable feature allows for highly precise comparison between individuals and items, simplifying the evaluation process. In addition, the RASH model provides a common scale for comparing individual and items, which the case of multiple tests or assessment use measure the same construct. Thanks to this common scale, users can make direct comparisons across tests. These two advantages can help school or teachers to better assess students' learning outcomes in practical applications. Efficiency is also another advantage of RASH model. The RASH model uses data efficiently, which means that it can produce reliable estimates of ability and item difficulty even with small sample size. This is because the model estimates each individual's ability and each item's difficulty separately, using all available data. The RASH model is easy to interpret compared to other models. The models produce clear and straightforward results, which can be easily understood. This allowed the model to be used in educational setting. For example, a teacher can easily understand the result of a RASH model analysis of a test and use the results to inform their instruction. However, the RASH model is not without its limitations. A key constraint is the assumption of unidimensionality. Since the RASH model is designed to analyze tests measuring a single underlying construct, the model may falter when applied to tests assessing multiple dimensions or constructs. This limitation can limit its application in certain situations. Another drawback is the model's assumption of local independence. The RASH model presumes each item to be independent of all others, given that the underlying construct has been considered. In practice, the assumption may not always hold. To navigate the RASH model limitations, users should keep the following recommendations in mind. First of all, selecting models function based on measurement objectives. It is essential to choose appropriate RASH model function based on the specific measurement objectives of study or assessment. The RASH model is designed to serve specific purpose. Therefore, it is crucial to ensure that the chosen model function aligns with goals and nature of data. Secondly, utilizing multidimensionality tests to analyze the dimension included in the objectives. Researchers and practitioners should use statistical tools like multidimensionality tests to determine if the data contains more than one dimension, which may impact models' performance. If necessary, consider other models or adjust RASH models to account for additional dimensions. In conclusion, although RASH model has its limitation, it can be effectively used in research and practice by taking certain measures. It remains a powerful tool with many advantages and is highly suitable for application in the educational settings. That's all. Thank you.